Number 1. Describe why the horizontal line test is an effective way to determine whether a function is one-to-one. So if you have a one-to-one function, f of x, is one-to-one, let's say, then that means that f of a equal to f of b implies, this arrow pointing to the right means implies that a equals b. Okay, but suppose you have a function that's not one-to-one. So let's say f of a equal f of b but a does not equal b. Alright, well then a horizontal line y equals f of a, say. Now this, a horizontal line has the form y equals some constant. Alright, f of a would be a constant value. Alright, it would be a definite value. So if you set y equal to f of a, call that that would be a horizontal line. Alright, that will intersect these two distinct points distinct or different. A f of a and b f of b. Alright. Now that would indicate that the function is not one-to-one. Okay. So for example, if you have y equals x squared, that's not one-to-one. There's your parabola, y equals x squared. So let's say this is a, and let's say that's b, and let's call that f of a, which happens to equal f of b. See, f of b is the same as f of a, but a does not equal b. So if you draw a line, horizontal line, y equals f of a, it would look like this. It would go through there. These 2 points here are distinct. That's point a f of a and b f of b. So a horizontal line y equals f of a will intersect the 2 distinct points. They are distinct because this is not a one-to-one function. Alright, so that shows you why the horizontal line test is effective in determining whether the function is one-to-one or not. Alright, so if it's not one-to-one, it will intersect these 2 points which would be distinct or different. Alright? Number 3. Can a function be its own inverse? Explain. Alright, so sure. So you could take f of x equals x. And that's also equal to f inverse of x. So f of x, so x, when you apply f of x, to x is taken to f of x, which equals x, and then f inverse applied to that will take it back to x again. Alright, you have to think about that a little bit, play with it a little, and you'll see, yeah, that works. Alright, so it's its own inverse. Number 5. How do you find the inverse of a function algebraically? So you have some function f of x. Okay, so you replace the f of x with y, then you interchange x and y, and then you solve for y, and finally you replace y with f inverse of x. Alright, so that may sound a little bit complicated when I just state it like that, but when you follow it step by step with an example, it'll make sense. Alright, you'll see clearly what to do. Now the book's answer, the one that I downloaded in 2018, summer 2018, has just y equals f inverse of x. Alright, so that's kind of a very brief answer with no explanation. So what I just said is correct. Alright, and you'll see in the next few problems we're actually going to do it. Alright, so that's it. Okay, number 7. For the following exercises, find f inverse of x for each function. So we're going to follow the format I was just talking about in problem 5 to do this. Alright, so we have f of x equals x plus 3. So first you replace f of x with y. So you got, instead of f of x, you write y equals x plus 3. Now you interchange the x and the y. Alright, so everywhere you see the x and the y, switch them. X equals y plus 3. Then you solve it for y. Okay, so you subtract 3 from both sides. X minus 3 equals y. And then finally you replace y with f inverse of x. So I'm just going to write that first. F inverse of x equals x minus 3. Alright, so there's f inverse. And there you go. Number 9. We have f of x equals 2 minus x. So you replace f of x with y. Then you interchange the x and the y. Then you solve for y. So you can transpose the negative y to this side and transpose the x to that side. Alright, so negative y becomes y over here. Transpose the x, that becomes negative x over here. And then finally, you write f inverse instead of y of x. F inverse of x instead of y. So f inverse is 2 minus x. Number 11. We have f of x equals x over x plus 2. Alright, so you write y instead of f of x. and then you interchange the x's and the y's. Alright, so you've got two x's here, change those to y's, change this y to an x. Now you solve for y. So to do that, multiply both sides by y plus 2. Alright, these will cancel. And that leaves you with x times the quantity y plus 2 equals y. Distribute that x through, so you get xy plus 2x equals y. Alright. Now what I want to do is isolate the y's. So I'm going to subtract y from both sides and subtract 2x from both sides. Or think of transposing this to the other side. Make it a negative y over here. And transpose the 2x, make that a negative 2x over here. So you've got xy minus y equals a negative 2x. Alright? So you want to isolate the y, so you factor the y out of these two terms. So that's how you would do that. Now you have one instance of a y there, and that leaves you with x minus 1 in parentheses. Like that. Then you divide both sides by x minus 1. And these cancel here and here. So that leaves you with just y. Negative 2x, y is equal to negative 2x over x minus 1. Alright? So that's the general strategy that you would do, or that you would use for solving or isolating a variable when there's more than one instance of a variable. Alright? You would clear any fractions, and then you would distribute, and then you would get all the y's together on one side of the equation and everything else on the other side. When I say all the y's, I mean every term in which y occurs, get it to one side. And then you can factor the y out using common factoring. Okay, that's and then finally you can isolate the y's like this. Just divide both sides by whatever you need to do and get the y all by itself, and you've got it done. Alright? Okay. Number 13. For the following exercises, find a domain on which the function f is 1-to-1 and non-decreasing. Write the domain in interval notation. Then find the inverse of f restricted to that domain. So we're going to be given functions which are not 1-to-1, but they can be made 1-to-1 if you cut off parts of the domain. Alright, for example, if you have y equals x squared, the parabola, if you restrict the domain going from 0 to positive infinity, you're just basically cutting off the left half of the parabola, and you've got the right half, which is increasing. Alright, and it is 1-to-1. Okay, the left half of the parabola is gone when you restrict the domain. Okay, so that's what we have to do here. So we've got f of x equals x plus 7 quantity squared. Now this is the parabola, y equals x squared, but shifted to the left 7 units. Shifted to the left 7 units. Okay, so we have basically two halves. We can restrict the domain for the left half of the parabola. Left half is on this domain from negative infinity to negative 7. The right half is another part we can restrict the domain to. That goes from negative 7 to positive infinity. But what we want is something that's non-decreasing. All right. The left half is decreasing. Okay. So we want to get rid of that part. So we just want the right half of this parabola. So that would be our domain. Okay. So that means x would be in this domain. This Greek letter epsilon means is an element of or is in. Negative 7 to infinity. Alright, so that's our new domain. So instead of writing f of x equals x plus 7 squared, we're going to change that to y equals the quantity x plus 7 squared. Alright. And we have the domain x in negative 7 to infinity. Alright. Now you switch the variables. Alright. Change the x's to y's and the y's to x's. So you've got x equals parentheses y plus 7 close parentheses squared. Also change the variable here as well. Now we have y in the interval from negative 7 to infinity, including negative 7. Alright, so now we're going to take the square root of both sides, and don't forget there's a positive and a negative square root. For example, if I say what's the square root of 9, you would probably immediately say 3, but there's also negative 3. That's a negative square root of 9. Alright, so because negative 3 times negative 3 also equals positive 9. So we have to consider both of those. So when you take the square root of both sides, you've got plus or minus the square root of x equals, and then take the square root of this, which becomes y plus 7. Alright. Now you solve for y. Subtract 7. So you've got y equals plus or minus square root of x minus 7. Alright. Okay. Now, which one is it? Well, we have to consider this right here. This little specification. Y has to be at least negative 7 or greater. Okay? So in order for that to be true, if you have the negative square root here, and you've got some either 0 or some other positive or some positive number, then if that's a negative, it's going to be less than negative 7. Okay? Well, if it's 0, it's going to equal negative 7, but if it's some positive number in here, and you've got the negative square root of that positive number, then it's going to be a negative number which is less than negative 7. Alright, so you need to disregard the minus or the negative square root and just take the positive square root. So that means f inverse of x would be equal to the positive square root of x minus 7, which you would just indicate by not putting any sign there at all. Alright, so that's the positive square root. Alright, so there's your f inverse. Number 15. We have f of x equals x squared minus 5. So this is y equals x squared. but shifted down 5 units. Down 5 units. So the non-decreasing part of this parabola has the domain from 0 to infinity. So x, this is in the interval from 0 to infinity. That's the domain we're interested in. Alright. So we've got, instead of f of x, you write y equals x squared minus 5. And you've got your domain x in the interval from 0 to infinity. Now you switch variables. And now instead of x, you got y in the interval from 0 to infinity, including 0. Alright? So you want to isolate the y, so you can add 5 to both sides. That leaves you with y squared equals x plus 5. Alright? And now you solve for y. Take the square root of both sides. So there's a positive and a negative square root, so you've got y equals plus or minus the square root of x plus 5. Alright? Now, again, we want y to be in this interval here. Alright? So if you take the negative square root, will that work? No, whatever this number is, when you take the square root, it's going to be negative, correct? So that's not going to be in this interval. So you take the positive square root, and that's f inverse. All right, so f inverse of x is equal to the principal or the positive square root of x plus 5. All right. Okay, number 17. Use function composition to verify that f of x and g of x are inverse functions. Alright, so the property that we're going to be using is this. If you compose f with f inverse, doesn't matter which order you take it, or which order you do the composition, the result will be equal and the result will always equal x itself. Alright? So that's a necessary and sufficient condition for a function, or for two functions to be inverses of each other. Alright? That's the property that you use to determine whether two functions are inverses of each other. So you have to do it in both orders to confirm that. Not just one way, but both ways. Alright? So let's try it. We've got f of x is equal to cube root of x minus 1. And we have g of x is x cubed plus 1. Alright, so we take f composed with g, and then we'll take g composed with f. Now if any one of these doesn't work out to be x, then we just stop and we know that they're not inverses. Alright, so f composed with g of x, that would be f of g of x. So that's f of, what's g of x? X cubed plus 1. Then you plug that into f of x here, so that's the cube root. And then x cubed plus 1 goes in the place of x there. Minus 1. So that's cube root of x cubed, which is x. Alright, so far so good. So that worked. How about g composed with f? We're not done yet. You got to do this part. So don't just stop halfway. That equals g of f of x. And that's equal to g of what? X, or cube root of x minus 1. Alright, so you plug that into there. So that equals cube root of x minus 1 quantity cubed plus 1. When you cube the cube root, you're just going to get x minus 1 plus 1, which of course equals x. So f composed with g does equal g composed with f, and they both equal x, so that means they are in fact inverses of each other. Which one would you call inverse? Well, if you start with g of x, you could call that g inverse of x. Or if you start with f of x, you could call that f inverse of x. Alright, it's up to you. If you want to do it in alphabetical order, which most people do, you start with f of x and you call that f inverse. Alright, but it's not incorrect to call that, start with g of x and call that g inverse. Alright? Okay. Number 19. For the following exercises, use a graphing utility to determine whether each function is one-to-one. Alright, so let's take f of x equals square root of x. Alright. Now you really don't need a graphing utility to do this one because this is one of your toolkit functions. Alright, you should know this by heart by now. But anyway, we'll just follow directions. And ours is not to reason why. Ours is but to do or die. Isn't that right? Haha. Anyway, for this one, yeah. Okay, so here's the graph. On my computer, it looks like this. Now, let's see if I can get this still here. There you go. Alright, so think of the horizontal line test. Will a horizontal line intersect that graph in more than one spot? No, I don't think so. Alright, so that is one-to-one. Number 21. F of x is equal to negative 5x plus 1. Oh my goodness, this is so difficult, right? This is a straight line. Y-intercept is at 1 and a slope of negative 5. Alright, you could draw this by hand, right? You should be able to draw this by hand. If you can't, you need to go back and review a line written in slope-intercept form, okay? And I'm serious, really, I'm serious. You should review that, and you should be able to do this one by hand. You don't need a grapher or a computer to do this one, all right? So, you know, you would think they'd give you something really nasty so that it would justify using a computer or grapher. But no, this one you could do yourself by hand, okay? So, however, just to play along here and, you know, be one with OpenStax here and do what they say. We've got a computer image here. Alright, here we go. Here we go. Are you ready? There it is. Just like I thought it would be. I told you. I told you. See, there you go. Now, is that one-to-one or not? Well, draw a horizontal line. You see a lot of horizontal lines on this grid pattern here. Do any of them intersect the graph more than one time? No, I don't see anything going on there. All right, so yeah, that is a one-to-one function. Okay. All right. In fact, the only line where you would not have one-to-one going on would be a horizontal line, right? Okay.